In the previous videos, we had discussed about electromagnetic effect and inductive effect. In this video, we are going to be talking about resonance structures. The reason we are talking about resonance structures is because resonance effect or mesomeric effect is one of the electron displacement effects in covalent bonds. So let's start. Resonance effect, or rather resonance structures, are basically given because one of the structures or the structure which we come up with is not enough for describing the various properties of that particular compound. For example, carbon dioxide. Carbon dioxide, we know the structure of carbon dioxide is CO2. So oxygen is capable of forming 2 bonds, carbon is capable of forming 4 bonds, and it's all good. But they found out that the bond length is 115 picometers between carbon and oxygen. So if there was a carbon oxygen double bond, the bond length would have been 122 picometers. And if it was a triple bond, then the bond length would have been 110 picometers. But 115 is basically in between these two values. And so this particular structure of carbon dioxide does not explain the property of bond length, and that is where resonating structures come in. So resonating structures are basically various structures which describe all the properties of the compounds, and they are the resonance hybrid of a particular of each other. So in case of carbon dioxide, so you have 2 electrons, right? Sorry, 4 electrons, and then 4, that's 8, it forms the octet. So if one of the bond shifts to the other, so let's assume this shifted here, or rather in reality it would have been this shifting here and this shifting here. That leads to the formation of carbon dioxide with a triple bond. Whereas another structure can also be formed with the positive charge on the left side. And this in turn was able to explain the properties of or rather the fact that the bond length of carbon dioxide is 115 picometers. Another example comes to mind. This is benzene. Benzene's molecular formula is C6H6. We know that benzene consists of double bonds which are basically at alternate positions or at alternate carbons. So scientists thought that we'd have 2 different bond lengths that would be observed. So that would be carbon-carbon single bond and carbon-carbon double bond. Carbon-carbon single bond's bond length is 154 picometers, whereas in case of a double bond, it's about 134 picometers. But it was found that in benzene, the bond length is uniform and it's 139 picometers. So we did not have 2 separate kind of bonds, it was just one, and basically it was neither a double bond nor a single bond, and that meant that these electrons are delocalizing and they keep exchanging, and that leads to the difference in the bond length. So that meant that led to formation of 2 different resonating structures. Carboxylic acids also have resonating structures. So we have RCOOH. So you have 2 electrons here. So this electron shifts and this moves here, and that leads to RCO minus OH plus, because there's a double bond. So here also this led to 2 different resonating structures. Now another example is aniline. We learnt about aniline. Aniline is basically a benzene molecule, C6H5, and that's attached to an NH2. So So this is the benzene ring, and to it one of the carbons, and NH2 group is attached to it. So when we learned about so NH2 is basically going to be electron releasing because of the presence of two electrons. So this will move here. This electron pair is moving towards this carbon atom, and so this leads to the formation of a double bond between NH2 plus, because it has a positive charge, and a negative charge on this carbon atom, and the other two bonds stay the same. Now what will happen is this electron will come in here, and this will lead to the formation of a bond between these two, but the tetravalency of the carbon atom has to be maintained. So here you have, let's take this carbon atom. This carbon atom already has 3 bonds plus 1 which is attached to hydrogen. Okay, so when this electron, this has a negative charge, when this electron comes in and forms a bond between these two carbon atoms, obviously it leads to the formation of 5 bonds, right? So 1, 2, 3, 4, 5. So the tetravalency of the carbon atom is lost. So because of that, to maintain this double bond is shifting to this carbon atom. That is why there is a movement of electrons taking place. So here this double bond is shifting and moving, and this position, the fourth position, gets a negative charge. So you have a negative charge at the fourth position, double bond here because this negative charge shifted down, NH2 plus, because it has 4 bonds. Now this electron will again shift here, and because this carbon atom cannot bear more than 4 bonds, this bond is shifting to give a negative charge over there. You have a double bond NH2 plus. Now what happens? This comes in here, this goes here. That leads to the formation of another resonance structure, NH2. So if you notice, this and this, basically there has been a shift of double bonds. So I will write another one. So this was for aniline. Let's do the resonating structures for phenol. In phenol, you have an OH group attached to the benzene ring, and OH is also going to be electron releasing in nature. So let's start with OH, right? So, and double bonds here, here and here. Now first, so below each structure I will also write the carbon atoms which are involved. So here we have these carbon atoms are going to be involved, and because this carbon atom is already bound to an OH, it does not have a hydrogen attached to it, but this one does. Now what happens is, the OH group gives 2 electrons to this carbon atom, and puts its electrons here, and this leads to the formation of a double bond. And because here you have 2, if you have 2 plus 1, 3, 4 and 5, the tetravalency is lost. So this bond is going to shift onto this carbon atom as a negative charge. So here you have the first step, and then these electrons or the bond is shifting to the carbon atom to give us a negative charge. Next, you have the same, let's just draw the benzene ring, and then you have double bond OH, and because oxygen is bound to 3 atoms, it gets a positive charge. And here you have a negative charge on this carbon atom, and double bonds stay the same. Now let's write the structure. So you have CH, then you have C, a double bond C, H, and a H. Now this negative charge is going to shift to this between these 2 carbon atoms, and that leads to the formation of a double bond. Then this double bond is shifting towards this carbon atom because again tetravalency, and so it shifts to give a negative charge over here. So this goes in to form a double bond, and this next forms the negative charge. So this will lead to the negative charge being at the 4th position, and you have the OH with a positive charge. Now here we have this carbon atom bound to a hydrogen, possesses a negative charge. You have this carbon atom, then a hydrogen, then it's one. Now this negative charge is going to move towards this carbon atom, and then because again the valency of this carbon atom should be maintained, this bond is going to break and it will lead to the formation of a negative charge over here. And that is what we will be writing over here. So you have a negative charge here. So here this went here, and at the 5th position you have, 6th position you have a negative charge. So our bonds, double bonds, are shifting. Now let's again write the carbon atoms which are involved in this transfer. So you have a hydrogen, here you have another carbon. So this carbon atom has a negative charge, and when this moves here, again to maintain tetravalency, this double bond is broken and the electrons are going towards the OH back to the 1st position. And that is how you write the resonance structure for a substituted benzene ring. So the different resonating structures contribute to the stability, and there is actually going to be the difference between the energies of the actual structure and the lowest energy resonance structure. So generally lower the energy of the structure, more is the stability, and the difference between these two is called as resonance stabilization energy. So there are various rules for writing resonance structures. First of all, you have to have the same position of the nuclei. Notice in no case did I change the position of the atom. It was only electrons which were moving around, and there are same number of unpaired electrons. That is what we followed all throughout. You have two electrons over here. The 2 electrons were the ones which led to the formation of so many resonance structures, and all the structures should have nearly the same amount of energy. Then all the atoms should have an octet of electrons except for hydrogen, which is exactly why I told you tetravalency of the carbon atom has to be maintained, because if tetravalency was not maintained, then that would have led to the formation of another thing apart from the octet. So octet has to be followed in case of other elements. In case of hydrogen, is going to be a duplet or doublet. So octet rule cannot be violated. Now that one of the examples for that is, let's assume you have CH2 bound to another CH, which is bound to an NH3 plus. Now to shift, we will shift these electrons here, and this would lead to the formation of CH2 with a positive charge, then CH and double bond NH3. This, however, is not a resonating structure because nitrogen has 10 electrons. So 3, 4, 5, 6, 7, 8, 9, 10. And 10 electrons, you cannot have 10 electrons. Because of that, this resonating structure is not even considered because the octet rule is not followed. In the next video, we will be discussing about resonance effect or mesomeric effect.